Imagine trying to teach a machine what an orange is. Since computers only speak math, they don't have eyes or taste buds to help understand. We have to teach them to tell the difference between the color orange and the fruit, entirely by looking at the company those words keep. The older way mapped clicks by following one single student around all day, noting who they talk to. You see who they sit next to, but completely miss the big picture of what the rest of the school is doing. A model called GLOVE takes a different path. Instead of following one word at a time, it looks at the entire network at once, a global view of every connection. It's like downloading the school's entire text message history to see everyone's interactions in one massive spreadsheet. Because the computer does all this heavy mathematical lifting up front, it can process entire libraries of text incredibly fast compared to reading word by word. To build this master spreadsheet, GLOVE starts by surveying a sentence to calculate exactly how close words are to each other. Take the sentence, "I like orange juice." Since orange and juice sit next to each other, they score a perfect 1.0. Orange and I are further apart, receiving a weaker 0.5. These scores are then plugged into a massive grid. This grid tracks every single time any word stands next to any other word across an entire book. By doing this, we've taken a flat written sentence and turned it into a highly structured mathematical map of relationships. There is a glitch in this system, though. Extremely common words like the and act like social butterflies. They are everywhere, standing next to almost everyone. These common words rack up millions of connection points, creating so much noise that they drown out the quieter, highly specific relationships that actually carry meaning. To fix this, GLOVE applies a mathematical balancing act. First, it ignores words that never cross paths. Second, it gently increases the strength of a connection as two words meet more often. This graph shows how that works in practice. The connection value grows steadily, but eventually it hits a hard limit. No matter how many millions of times the and appear together, their score is capped. Capping those hyper-frequent words keeps the system stable, making sure the real meaning in the text isn't lost in the background noise. Once the grid is balanced, the computer runs an equation that converts those relationship scores into literal coordinates in space. It turns text into a spreadsheet, and then turns those numbers into locations, projecting human language into physical geometry. We can see this clearly by taking this mathematical engine and feeding it the classic literature of Jane Austen. The computer was given 0 instructions about 19th century grammar, plot arcs, or character relationships. Any structure it finds is purely the result of tracking which words tend to appear near each other. This is the resulting map of Jane Austen's language. The words have organized themselves based entirely on how often they appear together in the text. Zooming in, character names like Elizabeth, Darcy, Jane, and Emma have naturally gravitated together. In another section, family roles like mother, father, and brother form a tight cluster. Over on the right, concepts like sense, sensibility, love, and happiness share a distinct region. Words that share contexts naturally converge. By simply counting how often words sit next to each other, we can translate the messy, abstract world of human thought into a clear, geometric map.